So today we have a longer class split into 3 parts. And then on Friday, there will be no class because I'm giving a lecture to Ferjut. So now let's go look at a bit deeper to the single step methods. So this is, remember, so these are a method for solving initial value problems. So we're solving the problem which is time derivative of equal some function of depending on t and y. Let's put initial condition like in a general form, and we what we do, we discretize this problem. So we take discretize, so it becomes single step method is it's very long arrow. So it becomes discrete, where in the first at the first point we take, well, this is what we take. Just let's write it the way around, and then yk plus 1 is yk plus h, some function of tk yk h. And so what we did here is that we took the timeline between the 2 points, so that t0 is associated, let's say, we integrate the equation between 2 points A and B. We split it into equal intervals such that the number of intervals is n capital. So this is t1 and so on. So what we have is that size of the time step is size of the interval divided by number of subintervals, and then so tk is t0 plus kh. Okay, and then k is from 0 to n capital. So this is a setting of a general single step method. So so there are several issues about this method we want to study. So let's first study some general properties. So first is an arrow bound. So arrow bound, we can directly give a theorem, which so what we need is we need to know how close is the solution of the one to the solution of the other, right? So we suppose the following thing. So first assumption is that suppose that this function phi is continuous. So in all 3 variables. So B is that it's Lipschitz. So you can see that Lipschitz condition is actually rather general. Is usually needed for this ordinary differential equation. So it's Lipschitz in Y. So that specifically, let's just write it exactly. So it's the values between the function and function at the same at different point, different y tilde, should be bounded by some constant by the distance between the 2 points. So this is for all y and y tilde. Well, in the space or in some domain. For some h, usually h is bounded by a certain number. This is convenient because usually we are interested in small h. And then time is where we're interested to to solve. So essentially, we have the Lipschitz condition in the domain we will want to cite the equation. And the last condition is that C is that the method is consistent. Remember, consistent means that phi coincides with f when h is 0. So consistent and has positive order. So positive order means, remember, so what it is, it means that if you compute solution at step h and subtract the solution that you would approximate with the single step method, so it's minus a minus h phi t y t h. So this quantity should be order p plus 1 in h. So it's order p plus 1 in h. In principle, it can be written as exact inequality. So it's smaller than dh p plus 1 for some d. Right? So this is for all times. And what and h. All in the domain, in principle, d can depend on yt and t. So important is that d does not depend on h. So d does not depend on h. But does not depend on h. Okay, so under these three conditions, so the first is just regularity, and the last is that method has certain order of accuracy. So then the maximum error, the difference between the computed and exact values is bounded by constant by hp. So and for any h, and constant that we can write explicitly. So it's d exponent m b minus a minus 1 of m. Okay, so long statement. Essentially, though, what is important is that if everything is regular and you have method of order p, which means that one step gives you an error p plus h p plus 1, then the error of the computation using the single step method is hp. And we can bound it even coefficient, theoretically. So that's why we put p plus 1 here, because at the end it's just for one step, and then the p appears here. So this is the observation that you can look is that why p plus 1 and p here is that because one step yields gives the arrow p h p plus 1, but we have how many errors? We have n steps, right? where n is b minus a divided by h. So the total error is h just p, because you see this one cancels with this h. So every step gives h plus p plus 1 error, but you have to multiply by number of steps. So you, assuming that errors accumulate, and then it gives you hp. So the proof is rather elementary. So let's do it once for this case, so we don't do it for other theorems. So okay, so first let's just write two relations. One relation is a method. So this is, and another relation is no. Not like this. So we have this. Let's give the name to this quantity. So let's just call it d. It will be. So let's take this quantity, but at each point, and then call it d tk y tk h. So that's this expression. So what it will be, it's different between t k plus h minus y tk h psi. So just denote this notation. Yeah, correct. So then what we do is we write two equations. One is our method. Good. And another is this expression, but written in a similar way. So we write here y tk plus 1 equal, so this term equal y tk plus h psi. Let's just add here that d by this condition is smaller or equal than d h p plus 1, right? So this is what we will use. Okay, so here we have tk h plus d. So this is deviation. Okay, now we subtract one from another and denote the difference by e. So e k will be yk minus ytk. So this is the error at times at step k. So when we subtract, we get this ek. So what you have is ek plus 1 on the left equal ek plus, then there will be h by difference of these 5 functions. And then this d term. So with minus. And now take a norm. And then take norm and use triangle inequality. Right? So it's small or equal plus h, then norm of the difference. Okay, just taking norm. Good. And then here we can use the Lipschitz condition, right? So we have this Lipschitz condition. So we get that minus 1, small or equal, then k. So Lipschitz condition will give us m, right? So plus hm, and then difference between the two. So this is again ek. And then for this norm, we also have a estimate. Okay. And now remember we had a general formula. So if you write this delta and this k, this was bad notation. So delta and this k star. So from this we can always write that ek is smaller or equal than E0 exponent n delta. No, exponent k delta. Plus k star over delta e k delta minus 1. So this was the general formula. So whenever you have this expression, we already derived that there is this condition. And then now we put back this k star and delta inside. So remember only that this is 0. Right? Initially at the initial point we take exactly initial condition, so there is no difference between these 2 points at 0. So that means that ek is smaller than this expression. I think it fits here. So that means that ek is smaller or equal than, so first k star divided by delta, so this divided by this. It will be d over mh. HP. And then there will be this exponent k delta. K delta is kh m minus 1. Good. So now remember that kh is smaller or equal than nh. And this is b minus a. This is size of the interval. So put here b minus h, and you get exactly what we wanted to have. M E M B minus A minus 1 HP. That's it. So relatively simple theorem. So what theorem tells that whenever we create a single step method which works on one step, it works also on a full interval. And if the step h is sufficiently small, we can control error everywhere. So this is an idea. So let's check it once for some method. Example. Second order Runge-Kutta, so we will see it in more general way, but we already had Runge-Kutta method that we obtained last time. So which was the method for the function phi in the form of f t plus h over 2, y plus h over 2, f ty. So this was phi. And we found that it's second order, right? So it's second order. So that's, so let's just check all the conditions. So first of all, condition A of this theorem, it's continuous if f is continuous. Right? So if f continuous, automatically this is composition, so it's continuous. Then B is the, so let's check that it will be Lipschitz if f is Lipschitz. So if f is Lipschitz, in Y, so constant, Lipschitz constant L. So let's assume that f is Lipschitz. Let's check that phi is Lipschitz. So you just have to take this difference, y t y h minus phi at t y tilde h. And we have to compute the difference. So how we do it? So that's difference between these two functions. So this is 1, and then we just subtract the same thing, but with the y tilde. Okay. Good. So what we have? So time is the same, argument is different, and we have that f is Lipschitz. So we just directly use the Lipschitz condition. So it gives you smaller than L by the difference between these 2 points. Okay. The next, we use triangle inequality. So we split one difference from another difference. The second difference will be and again, we can use this second time the Lipschitz condition. So again, L by 1 minus tilde. So this is equal to L plus L squared H over 2. And this is smaller or equal than m y minus y tilde. So what we need to take m, which is independent of h. So m we just take as L plus L squared H0, so the largest value that is allowed. So that's okay. So we found that it's, and generally the proof is the same. So for any method that, at least all other Runge-Kutta methods from them, they have this similar form, just more functions inside, so there are more compositions. But anyway, the Lipschitz continuity of original function implies Lipschitz continuity of the function phi. No, and of course, C is that it's consistent and has order p equal 2, as we checked the other time. So it means that in this case, the error will be of order h squared. Okay. Okay, so everything works. Everything works. So now, whenever you use this method implemented in some packages like MATLAB, Python, and so on, so Runge-Kutta method is the one that you often use. So you often use second, third order. So we will talk about this difference. And but usually, often for a nice problem where you have everything is quite smooth, it's popular to use fourth order method. Right? So it's probably the method that you use most of the time. So let's just show how you derive any Runge-Kutta method in principle, and then of any order, and then just check some details. So Runge-Kutta method. So what is good about this method is that they are high order. So they're rather accurate, and also they require computing only the function at some points. You see, this is what I want to say, that high order method, in principle, it means that the function is sufficiently smooth, has second, third, fourth derivatives, and so on. So in principle, you can create a method which is directly linked to derivatives. You can just expand it in Taylor series and integrate. But numerically, this is a trouble, because using such method means that you need derivatives. And derivatives can be costly. They also can be inaccurate. So there can be many problems. So the good part of Runge-Kutta is that you don't need to compute derivatives. You just compute the same function, but just in a few points. So let's see how it works. So the R stage. So R stage Runge-Kutta method can be formalized just as the function, which is sum of R terms. So our stage is essentially this. This is two stage. So you compute once and then another put it inside. So the stage is how many compositions essentially you do. So CK. So this is a function. This is linear combination of CR KR. So of terms, where KR is exactly what is what's linked to the function. So the K1 is original function, always. And then the general KR is a function computed at certain fraction of the step, of the time step, and the point which is separated from y by h by some linear combination. So it's s from 1 to r minus 1 with certain coefficients. And you see, so in order to compute next kr, you need to know all k previous k's, which you put it as an argument. So this is stage. That's why we say stage. So every time we iterate the function, but using the previous computations inside the argument. So this is a composition. Every time is a composition. So this is our compositions of the function. So coefficients. So what are the coefficients? So there are coefficients CR, ER, and the matrix of coefficients BSR, RS are chosen such that the method has an order, usually on order R. So we need to choose coefficients such that it gives you the certain order. So how to choose? And well, the choice can be done just case by case. Now, first of all, what you can see first of all, you can already guess, which is exactly can prove, but you can already guess a relation between A and B. Because A gives you a fraction of the step, and Ks is always a function. So H should be the same as H sum of the BRS. So the fraction of the step should be the same as the fraction of the step which is multiplied the function. So in all methods, AR is just the sum of this. So this is one rule, which is general. So this is for R. R starts from 2, right? So then the other coefficient, so then we have A, so we have now need just B's and C. And this can be done case by case. So R equal 1. So when R equal 1, there is no coefficients, because just this same function. And this is Euler method. So R equal 2. So the particular case you can take C0 to be 0, C1 equal 1, B21 equal 1/2, and then it gives you A2 equal also 1/2. So this is a function that you put it inside, and then you get phi as t plus h/2. So there is only, you see, only second term, right? So it's only C2 K2. So C2 is what? C1, C2. C2 K2, so F, and then Y plus H/2. Essentially, this is exactly the method we just took. So this is second order. Okay, good. But in principle, there are much more other methods. So let's just check that how you would proceed in general. So on this particular case R2. So what we will do, so this relation must be satisfied, but the others are not. So what we do is, so in general, so this expression gives you two terms. First with coefficient C1 by K1 plus C2 by K2. And K2 is already a function of T plus A to H. And then there will be Y plus this B2. Now it will be B to 1, but B to 1 is A2. So what you see is that actually instead of second order method in this form, in principle there are more different combinations, which gives the same order scheme. Right? So whatever. So far no. So let's find coefficient which will give the same order scheme as this. Okay. So what we need is, so we need to find coefficients which is C1, C2, A2 for the order b equal 2. Let's do it. The order of the method is the difference between, remember, t plus h minus yt and minus phi. H. And this should give us order h cube. Okay, so let's do it. So let's So let's expand. So first we expand y. So y is expanded as y of, in Taylor, yt plus dy dt, h plus 1/2 h square d2y dt square. So this is the first term. minus yt. So this is already will cancel. And then we put this phi, which is hold this expression there. Minus C2. Okay. So now remember that this is f, right? And this is a derivative of f. Yeah? So exactly, so this is dtf. So first term is f tyt h plus h squared by 2 derivative of f plus b minus this. And now expand this in Taylor. C2, so first take derivative with respect to time, dt by a to h, and then C2, yeah, something is missing. H, of course, is missing, okay. Certainly don't focus. So there's H here, H here, H here, H here. And then we expand also the second term. So plus, it's minus df dy h c1 f dy of t. So you see that this term, so there was also, I forgot this O of h cubed, but this term is the same as this because it's multiplied by h. Okay. This is so let's collect something. So let's collect at least these functions h f of t y of t. So this will be multiplied by 1 from here. There will be minus c1 from here. And minus C2, A2 from there. No. Minus C2. Yeah, we forgot here the function. We expanded, so there is F still. So 0 other term we forgot. So it's minus C2. Then there will be df dt. Then remember that this should be opened up, right? So it will be h squared over 2 df dt plus df dy. And then again dy dt, which gives f. And then there is still this term. Square. So it will be a2 df dt minus c1 df dy f plus hq. And now collect the other terms. So it's so this will be still hf t y of t y minus c1 minus c2. Then we collect df dt. So it will be h squared df dt. 1/2 comes from here. From here comes minus c2a2. And then we take h squared by the other term. So the 1/2 comes from the first term, and then here it will be plus should be minus. So it's plus. Yeah, so just confused here. So this is plus, of course, here, and A2. Can it be? Yeah, A2. Minus C2A2 again. And okay, so this is obviously equal second order method if okay, let's be careful. So if this coefficient is 0 and the other coefficient is 0. So if C1 plus C2 equal 1 and C2 A2 equal 1/2. Okay. So in other words, we can just say that C1, so there are two equations with respect to three unknowns. So one coefficient is free. So let's take C1 to be 1 minus alpha, C2 equal alpha, and then A2 becomes, from the third equation, become 1 over 2 alpha. So this is an arbitrary coefficient and general second order Runge-Kutta takes the form of phi equal, so first 1 minus alpha, this first coefficient by f, plus alpha, f, and here we have a composition. So this, so this is a more general form. So it's a two-stage method. So the alpha equal 1 gives you the same as what we did, this midpoint Runge-Kutta. So alpha equal 1 means that the first term cancels, so we have only the second term, and it's just 1/2, 1/2. So we just directly get this expression. And then, for example, if you take alpha to be 1/2, so this will be modified or improved Euler. So this is a method which you can derive in another way, kind of following the idea of Euler equation, but to the second order. So I will not write it, but alpha 1/2, it means that half of the derivative plus half of the other expression. So you see it will be t plus h, y plus h, f. Let's write it explicitly. So you see what the expression means is that it's like you take Euler approximation and then compute the function not only in the beginning but also at the end point of the Euler approximation, and then take the average between the two. So this gives you second order. This will give you second order scheme. And finally, let's just finish with this stuff and then make an interval. So this can be done. So similar analysis can be carried out bigger orders, for larger orders, and essentially this is more or less the same idea. You take linear combination and start to expand in the series just to see that all terms of up to a certain order should cancel, and this gives you a relation between the coefficients. So there's it's technical work, not very something special, and the most popular method, actually not exactly in this form, it's in a bit more advanced form that we will see, but it's based on fourth order. Fourth order Runge-Kutta. So fourth order, let's just write fourth order Runge-Kutta just as an example so far. So fourth order Runge-Kutta, so what it is, it's phi, which is h over 6, and then it's sum of k1 plus 2k2 plus 2 of k3 plus k4. So these are coefficients. And then I'll just write explicitly what it is. K1 is f, k2 is f at half step, this is K1, right? is the same. But you don't stop here. Then you take K3, which is just the same expression, but with next K. And then you compute K4 as F at the end. Okay, so you see some clever combination of the function with certain coefficients and compositions gives you high order method. So this is how it works. So there's none. You just instead of computing function once in Euler method, you compute it 1 to 4 times, and instead of first order, you get fourth order. So very cheap and very efficient. So let's make an interval. Okay, let's continue now. Okay, so we have a method. So now how it is usually implemented, especially in already the packages that you can find for the use in whatever this computing system. So usually it's used with it have to be used together with an error control. So we had a theorem that tells that error is good, but just if you go directly, it may be not very effective. So the problem is that we want to control error of the computation of ordinary differential equations. So it's the first statement that it's usually difficult to control. Practically control a global error. So it means that controlling the difference between the computation and exact value at all points of the computation. So it's usually controlling this quantity is difficult. Especially because, as you remember, there was because error can grow not only because the computation, but because the error that you obtain at every step evolve with time. Right? So, and for example, if the system is, as you know, if the differential equation is hyperbolic, then initial error, which can be very small after many steps, it can increase just because of dynamics, not numerics, but because of this dynamic itself. So usually how the error is controlled practically. So in practice, we control local errors, a local error. So error at one step. So we control the error. We put a bound on an error that obtained in one step, and kind of ignore the fact that this error then can grow, because this is usually what we can do. And this is sort of the practical. So how you do it? So so the practical scheme is that you do it in 2 steps. So first you compute so one step means between k and k plus 1. So compute next one approximation. So compute it with method of order p. And then you compute the same thing but with a different method. Of order, let's say Q, which is bigger. So since the order of the second computation is higher, so and the step is small, it means that the second value is much more accurate than the first. So the error is different. So you can approximate the error as a difference. See, because this is much closer to the exact value than this, so the difference is essentially it gives the largest part of the error. And then the condition you verify is that the required tolerance is written as that this should be smaller than some epsilon that is given, this prescribed. Prescribed tolerance, but now you see this is prescribed tolerance for the full computation. This is just one step. So in order to make it step independent, we multiply it by the step size. So then it becomes proportional to the step. So this is usually how you do it. So you prescribe the error. It can be absolute or relative. If relative, then you also put y, norm of y inside. And then you ask that this should be smaller than this value. And the typical method is uses adaptive steps. So adaptive step means reduce the time step if error is larger. So essentially what the usual methods are doing is that every time you make a computation, the way how you can do it, every time you compute the values with two different methods, with two different orders, check if the error is good or not, and if error is not good, so if this is bigger, then you just decrease this time step and do it again and redo. You can also do it in the opposite direction. So if this condition is satisfied, but satisfies too well, so the error is much smaller than this, then you can increase the time step. So this is what method with adaptive steps is doing. Most of these methods are adaptive steps that you can find in Python, MATLAB, whatever. And this is what they do. They change the time step so that time step adapts to the tolerance that you're asking for. So in principle, we cannot. This does not guarantee that the global error is also epsilon, but you can prove the global error in that case is C epsilon, with C independent of epsilon and h. So in principle, you can prove that if you control local error, that you, in principle, also control global error with some coefficient that depends on a system. So in principle, it works. So this scheme can be implemented in Runge-Kutta. It is what is called Runge-Kutta Fehlberg. So essentially, it's Runge-Kutta, which is kind of mixing fourth to fifth orders. So the reason why you need mixed fourth to fifth order is because it's costly to use different methods to compute one order in another. If it's just two different methods, that you do double job. So what this Runge-Kutta Fehlberg method, it gives you the scheme how with this essentially the same computation can give you both fourth and fifth order. So in that case, in that sense, it's convenient. So it's not so obvious because you remember that every order of Runge-Kutta are different combinations, and different combinations which are always compositions. So it's really some fine tuning of coefficients that gives you with the same terms with the two different orders. So what it is? So how you do? So remember that we need these k terms, which are compositions. So the k1 is original. Then k2 is already become a composition. K1. So it's different. You see, it's h over 4. And then there is k3. I'll show the next term just for you to see that it's becoming more complex every time. You see, it's composition with a linear combination, and so on. So then there will be K4, K5, and K6. So there are explicit formulas with certain coefficients which are computed with this analysis. And then this same case, they give you both fourth order and fifth order. The fourth order method is when you take this phi as, I will write it so you see the complexity. The one term, then 1, so it's 1, 4, 0, 8, 2, K3 plus 2, 1. So there's it's certainly not what you can guess. So this is the fourth order. So just take a combination of the 4. And you also take fifth order by a different combination. Let's see a couple. So this is probably one of the most popular methods which you use with packages because the computations that you do is fifth order, but error control is done by comparing fourth order and fifth order. So you can do it with adaptive step is adapted, and then by comparing you get. Okay. Good. So the next next topic I will tell you. So more in a general form about the multi-step method. So this was so far was single step. So now let's go to multi-step method. So every time it becomes just more complex. So multi-step methods. So multi-step method we can derive more or less in the same in the same shape as in the same form as we divided single step. So we approximate just to justify. So we approximate the exact equation. The exact equation is remember, so it's derivative integrated between two times, but now we integrate between two times, between time tj and tj plus 2. So between 2 points. And the right-hand side will be the same integral from the right-hand side. So what we do is that we use two-step. And exactly that's what was called Simpson method for computing integral. Okay. And this is just y at this point minus y at that point, so that it becomes y tj plus 2 equal y tj plus, and then, so if it's approximated by the Simpson method for this integral, and this is h over 3, if you remember, and then there are 3 points, t j plus 2 y j plus 2 plus 4 f in the middle point plus f at the last point. So that's it. So this is already two-step method because we approximate the new value from, well, formally from the 2 steps in our procedure. And what you can directly see from this expression is that the new value which we need to compute appears here and here. So let's just become yj plus 2 equal yj, right? So it appears here and here. That means that it's, in principle, can be implicit. So we need to, it's nonlinear equation. So every time you make a step, you have to solve this nonlinear equation with respect to yj plus 2. So it seems to be complicated, but that method actually have many good properties, especially in partial differential equations. So because they are usually much more stable. So that's different. So they're much more stable, and it turns out that actually it's not that costly to make this computation. But you can gain a lot of stability. The question that will come in a while. Just giving a general method. So in general, the k-step method has a form so you take some linear combination of the points on the left, and so putting all y's to the left. And the right-hand side will be h by the linear combination of f's, as you can see. So it will be h by linear combination of f's with another coefficients. Right, so f of j is f tj of j. So that's a general form of the method, and now you just need to choose right coefficients to give a right order. Right, so that's the whole stuff, and you can immediately classify them in explicit methods. Explicit. Explicit method is when you can directly resolve it with respect to the new value. It means that it should not appear here. So it means that explicit method corresponds to the case when beta k is 0. In that case, there is no need to solve nonlinear equations because there is the new value that you compute is here. Implicit method is the opposite case. Okay. And of course, it's k-step method. So in order to make the first step already, you need to have k previous values. So usually for initialization, we need what? So we need the k values. Right? K minus 1. Yeah? So we need k values. So when you use this method, for example, due to stability reasons, for example, that first k method can be computed in any other method, like Runge-Kutta, because the stability is what is important after many steps. So the first initialization can be done so use a different method. For example, the same Runge-Kutta. So you need to initialize, so you need the first k points, which you can use whatever method, and then you apply the multi-step. So this is another strategy that can be used. And as I said, the reason for using different applying method is often related to stability. So implicit methods are usually quite more stable. Yeah, so now let's verify this issue of stability. So what is stability? I will not give really stability theory, but just give you the idea where it comes from. Stability. So the best is just consider first example of unstable method. So let's solve the simplest situation. The trivial equation with trivial initial condition. So the solution should be 0. And let's apply the numerical method to this scheme. And we use two-point method. So what is two-point method is that yj plus 2 will be equal to two-point method. It means that there is no right-hand side, but there is a left-hand side. So it will be plus alpha 1 yj plus 1 plus alpha 0 yj equals 0. So this is how you compute. So having 2 points, you compute the third point, and so on. So a general so now if you substitute exactly 0, it will stay 0. But now assume that you have some error of the computation. So it will be not imaginary error. So you didn't know that you were, for example, exactly at 0 in the beginning, but just slightly different. So what will be the solution? So in order to see what will be the solution, let's just compute exactly what is exactly solution to this system. So you see, this system depends on 2 initial conditions. So essentially, you need 2 independent, and it's linear. So if you find 2 independent solutions, linear combination gives you the general solution. So the solution, but so we look first for particular solution. If you ever had stability theory, you know that it's a linear equation, so particular solution should be found in the form of a power law, z power j. So if you take z power j, substitute it here, so you get z power j plus 2 plus alpha 1 z power j plus 1 plus alpha 0 z power j equals 0. Cancel one of the z's, zj, so you get z square z plus alpha 0, which gives you two roots, z1 and z2. Let's assume that they're different. So since we have 2 roots, we have 2 solutions, and it gives us a general solution. The general solution will be yj equal to arbitrary constant by one solution, by arbitrary constant by another solution. Well, we just put arbitrary constant in the form a1h, just to show that. Remember that not put just a1, g plus a2 And now remember that, where J is what? So J is Tj minus T0 or H, right? No, that's way around. So this is computed at time, which is T0 plus JH. This is general solution. Okay. So now, what you see that if one of the roots is bigger than 1, and the coefficient is not 0. So if one of the roots, if you take a method with coefficient such that one of the roots is bigger than 1 in absolute value, and somehow coefficient is not 0, which is always usually true because the numerical, you can obtain by numerical arrow, then Yj goes to infinity in norm as h goes to 0. So whenever you want to compute result at fixed time by reducing h, you increase power j, and then it means that whatever error that you obtain because of the numerical instability, it will grow to infinity. So what happens is that reducing the time step instead of improving the result, it will make it worse. And so what usually you observe numerically is that your result is exploding. So you just give a small time step, expecting better result, but if the method is unstable, the result will explode. So in general, what is the philosophy here is that in general, so let's start with a single step method. So a single step method gives us a new point in terms of the previous points. So what you see is that so you can look at this relation independently on the equation of motion that of the system that you was approximating. You can just look at this relation as a dynamical as a system which has some dynamics with increasing k. And as the system by itself, it can be stable or unstable in the following way. So imagine that you have two close by points, y0 and z0. So what you have is that then there will be next points, y1, z1. Then there will be next point, z2, y2, etc. So the question, will they stay close or diverge? Just by itself. So irrespective of the system which was original, just we take this phi, will they stay close or they will diverge? So if they stay close, the method is stable. And if they diverge, the method is unstable. So that's essentially the idea, is that in a stable method, whatever error you take, it will not close or diverge as h goes to infinity, or to 0. So increase step. Probably I was a bit confusing in this part. Read the book anyway, but once to understand. This is a complicated topic. So the idea is that the idea is essentially the difference between the associated between the step which is small. So the difference is that which exponential. Probably next class I will repeat this topic. But so the idea is that the instability in this system is usually exponential. So whenever you increase h, the error that you obtain improves because it's higher order method, right? So improves as power of h. But if the method is unstable, then just by iteration, the error is increasing exponentially as h. And exponent is stronger, right? So that's why exponentially is 1 over h. That's why if the method is unstable, though you reduce error by taking smaller steps, but this error will be later amplified much stronger by the iterations. So there is a competition. That's why if the method is stable, it will work because you decreasing step, you improve the accuracy of each step, but then this error will not grow. But in the unstable method, you get much better approximation at each step, but this small error will be amplified exponentially fast by the fact that decreasing the step, you have more steps. Yeah, so that's a competition which gives to the failure for the unstable methods. So let's just compute. Well, let's just show that the single step method works. Single step method. Okay, so what we have is that we have two methods. We have the same method, but starting with different points. And just the same thing, but with different point. Different evolution, which is close by. Okay. And let's take a difference. So we have y k plus 1 minus z k plus 1. Y k k. H phi like this. And now take a norm. remember that this is a Lipschitz function, so this can be written as small or equal than h m yk minus zk. So this has become 1 plus hm yk minus zk. And this can be iterated, right? And so whenever you iterate it, then you get yk minus zk in a norm. It should be less or equal than 1 plus hm norm of the 0, and this is less or equal, so this can be k times. And this should be approximated as exponent. So this is hmk. Like this. And now remember that this can be approximated. K is small or equal than n. So this E H N M. And Hn is an interval. So that's it. So this is independent of H. That means that single step is stable. Single step method is stable. So in that case, decreasing H does not lead to the increase of an error. So in this case, it's stable. Okay, so I myself a bit confused. So I'll repeat. We come back to this issue again in the next class. It's not a good idea to give a long class, no? Okay. So now I'll just give you the very last part. So stability we discuss more later, just to digest it better. So the final part, which I would like to give you, is the predictor-corrector method. So predictor-corrector method comes from. So the idea is coming from a fact that we need to from implicit method. So predictor-corrector method is kind of combination how you can combine explicit method and implicit method, partially implicit method, so that it becomes implicit by, explicit by form, but implicit by nature in a sense. Okay, so let's take implicit k-step method. So this mixing implicit, explicit. So what it is, so let's already write it in this form. So the first coefficient will be 1. Then we take L from 0 to k minus 1, alpha L, y g plus L. So this is the left-hand side, and then the right-hand side. So if it's implicit, so then the first term should be not 0. So this is not 0. So in order to motivate this predictor correction method, what would be the way how you solve this? So normally, how would you solve implicit k-step method? You have to solve it with respect to this variable. Right? So it comes on the left-hand side and right-hand side. So we can solve it with iterative method. Remember, this is non-linear equation. We have an iterative method how to solve. So the way to solve is take initial guess. The good initial guess is just previous step. And then put it on the right-hand side, compute the left-hand side. Put it on the right-hand side, compute the left-hand side. And we know that under good conditions it converges if you're close enough to the solution. So then the iteration is that the s plus 1 iteration you find from the by putting this term on the left. So it becomes minus sum from 0 to k minus 1. Plus h beta k f tk. So here it's important that we put previous iteration term here to compute the next iteration. And then this term which doesn't change again. So that's how you would work with implicit method. And in fact, whenever you solve ordered differential equations, the steps are small. And if the steps are small, then already this is a good approximation. And the implicit method converges very fast. So essentially, it's just 1-2 steps is enough. Practically just 1-2 steps, and you already have a good approximation. So this means, so how you go to the predictor correction method is that essentially we combine one step of the implicit method, but in order to have just one step, instead of taking the previous guess, we take beta guess here. So we take a guess obtained by explicit method, and then single step was implicit, and this gives you prediction correction. So that's a clever trick. So how you do it is you have a predictor step, so P. So for predictor step, use a better explicit scheme method for initial guess. And then you use corrector which is just single implicit single iterative iteration of implicit method. So usually this should be order p minus 1, the second order p, and this then the method is order p and stability properties of the corrector method. I'll give you an example, but so the idea is that idea is essentially that we want to use explicit method because it's better in a sense. It's often more stable, but we don't want to solve equation because probably of explicit method that you need to solve nonlinear equation. So we, instead of solving nonlinear equation, we do a trick. So we make a first guess much better. We use some other method to get a first guess. It can be done with any other method, explicit one, because it will not lead to instability. It's just guess. And then we use the iterative step just single time based on the nonlinear or on the implicit method. So let's just give us, and what you can prove is that for the guess you can use the method which is one order less. Yeah, so this is how you these are ingredients that you need to put it together. So by form it's explicit because the right hand side now is explicit. You don't need to iterate and converge, but it has properties of the stability properties of the corrector and okay, and order p. So just let's give us example, and that will be enough. Example. Euler trapezoidal. So how you do? You first make a prediction. The prediction step is just Euler. So that's prediction. And then you put a corrector. So Euler is the first order. Order 1. And then it means that we need order 2 for the corrector, and then we take this, so it will be yj plus 1 of the corrector. It will be yj plus h over 2, and then we take j plus 1 fj plus fj, where this is computed as with the previous value. So you compute first predictor and then you correct this value once again, because you put it inside the function and compute it with a higher order method. So if you just use the second line, it would be implicit scheme, because yj plus 1 comes in two places. But you split it by computing this with one order less, but still better than just 0 method. Put it inside and then come here. So it gives you second order method. So this is order 2. And which gives us order 2 in total. So though, despite you used order 1, but at the end you get the order 2. So this is, though it looks complicated, but this is often used in partial differential equations, because in partial differential equations, the nonlinear evolutionary equations, you often will encounter problems with stability. And stability will be maybe one of the biggest issues. So this is one of the ways how you avoid instability from one side and complications with the solving equation of implicit method. So it by form it's explicit, but by nature it's like implicit. Okay, let's stop. So what I think I will try to tell you next time is I'll try to come back a bit to this question of stability. I think it's good to revise it once again, just to understand the concept. So because the concept of stability is somewhat it's different from accuracy. See, so there's one thing is just accuracy of each step. It's how well you approximate the original equations, and stability is a slightly different concept. It's not how well you approximate one step, but whether the small errors which appear will grow will be amplified by many steps of the method, because refining the mesh, you're making more steps. So when you refine the mesh, you have more steps. So if there is exponential increase of small error, it doesn't matter that the error decreased with a small step, but it will be amplified exponentially. So whether this will happen or not, so that at least conceptually that you should understand what does it mean. And I think that I'll tell a little bit about stiff method that is also very practical. And I think that we finish.